right, in this example, we've got two fractions. They happen to have sign in your denominator. But you're going to follow the same rules as typical. You've got two fractions. We're adding them, so we need a common denominator. And if you've got two binomials, they have nothing in common. And even though they have a sign, they don't really have a common factor. That's really the key thing. You can always just multiply these by each other. And that's really going to probably be the way to go here. So 1 minus sine x on top and bottom on this side. Multiply that side by 1 plus sine x on top and bottom. And then let's multiply everything out, see what it comes out to be. So first up, we got 1 minus sine x times 1. Now 1 minus sine x times 1 plus sine x, those are differences of squares. So the 1 and the 1 multiply together. The middle terms are going to add to 0, so they're going to go away. And then you're going to have minus sine squared x when you multiply these two terms together. Now, over here, you're going to have the exact same denominator, so I'm just going to go ahead and do plus and extend the numerator out. And on top, you've got 1 times 1 plus sine x, so go ahead and add that in. Now, the trickiest thing about these is you want to take them as far as you possibly can. Get them simplified down as far as possible. Sometimes that's not clear, so just keep looking to see what you still can do. So at this point, we got 1 plus 1, so that's 2. Negative sine x plus sine x adds to 0, so that's gone. Now on the bottom, 1 minus sine squared x, that can be simplified. So back to our little corollary, we keep coming back to this Pythagorean identity. I say corollary because it's not part of the main problem, but it is a true statement. We can use it as an identity to simplify this down. You can subtract sine from both sides, sine squared, and you'll see that 1 minus sine squared x is equal to cosine squared x. So that's a little bit simpler, so I'm going to do that. Go ahead and replace 1 minus sine squared x with cosine squared x. And this can go even further because we're dividing by a cosine. Anytime you can make something not be a fraction, that's always best. Everybody prefers things to not be fractions. So 1 over cosine is secant. This is squared, so it's secant squared. So 2 times secant squared x. And I don't see anything else we can do at this point, so that would be good enough. That would be as far as you can take it. This example is just to write in a form that's not a fraction. So we're going to be looking for a way to make this denominator go away. And a good big hint is going to be something we just did on the last problem. We have 1 minus sine squared, that could become cosine, and then that could be divided out. So let's see if we can make that happen. And we'll take the same approach. This is 1 minus sine x. So I'm going to multiply by 1 plus sine x. Now in your homework, just keep in mind, sometimes these, you just got to try things and play around. It may not be super clear right away what to do. You're going to learn just as much from trying something and hitting a dead end as from just, actually going to learn more that way than just me telling you what to do on these. So part of the experience is just playing around, trying stuff, and ultimately having to start over. That's just how these problems tend to go. But the most direct way to handle this one is to try to turn this into cosine, and that's going to happen by multiplying this by 1 plus sine x at the bottom. All right, and what my strategy is here, those are conjugates of one another, and they're going to lead to 1 minus sine squared, which is cosine squared. And that's again from what we just saw in the first example. So let's multiply this out, see what happens. On the top, I could distribute, there's nothing wrong with it. Just knowing where this problem's going to go, I'm going to leave them separated for now. So I'm going to get to cosine squared x times 1 plus sine x. Nothing wrong with distributing. It's just, this is going to make this a little bit simpler in a minute. All right, these, just like on the last example, it's going to come out to be 1 minus sine squared x when you FOIL it out. The middle terms will add to 0. Now, since it's 1 minus sine x on the bottom, sine squared x, from the same thing we did earlier, this can be turned into cosine squared x. So on top, cosine squared x times 1 plus sine x, all over cosine squared x. And since that can divide out and become 1, you're left with 1 plus sine x. So hopefully it's kind of clear where this would be useful. This is a lot simpler to deal with than this big fraction right here with something that's already squared in several parts. And you can probably kind of anticipate when you get to calculus, if you have the option between doing this problem or doing this problem, you're looking at probably a page of work here versus just probably a couple lines, maybe even something you can do in your head with this one. Final thing to talk about today is the limit notation. I just want to keep reiterating this idea as x approaches something, what is your function approaching? In other words, this would be the y value because cotangent of x would be the function we're looking at. The extra piece here is that this is pi with a little plus sign. So before I get into what that means, let's just take a look at the cotangent function. And I want to make sure that I graph a piece of it that has pi. Now, cotangent, you have an asymptote at 0, and you have an asymptote again at pi. So right away, I'm kind of seeing that this problem's asking me about what's going on with that asymptote. It's looking at that barrier, kind of trying to check out something. Now, cotangent at pi over 2, you're at 0, and it sort of looks like a negative x cubed function. Now, for the sake of this problem, that's good enough for what I need. I don't really need to graph an extra section, but if you want to, you can. So, back to what this is asking for. As x approaches pi with a little plus sign. Now, what that little plus sign means is on the positive side, or the right side. And in a second, you'll see one with a negative sign. That just means on the negative side or the left side. So as x approaches pi from the positive side, so you almost have to think backwards here. As you're coming this way, you're getting closer to pi, but on the right side, on the positive side. What are your y values doing? Okay, well, your function just gets higher and higher and higher, so your y values are approaching infinity. On the second part, as x approaches pi to the negative or left side, what's your cotangent function doing? Okay, well, if we're on the left side of the asymptote, because pi is right here, well, our y values are getting smaller and smaller. They're getting really close to negative infinity. And that's really all you got to do on that.